Hi, this is Maria, and I just wanted to tell you a little bit about the applications of intermolecular forces. Do you remember? If you have no idea what I mean by intermolecular forces, probably be a good idea to rewatch that Intro to Intermolecular Forces video if you need just a bit of a refresher. All right, two major goals, talking about the effect of more or maybe stronger intermolecular forces have on the property of a molecule. And then really to clarify the difference between dissolving and dissociating in water, because it's a common mistake that people tend to make. All right, very quick review. London dispersion force is the weakest temporary dipole, and it's found in all molecules. A lot stronger is dipole-dipole interactions. They're found in polar molecules, still an electrostatic type of attraction. The hydrogen bonding is found in polar molecules that have a hydrogen directly attached to either nitrogen, oxygen, or fluorine. Do you remember it has to be a polar molecule in order for hydrogen bonding to be occurring? And also remember, hydrogen bonding, not a bond. It's an interaction, and it's the strongest out of the three here. So when we're talking about melting point, boiling point, and the effects on the effects by intermolecular forces, it's important to kind of be like, oh, okay, well, what's melting point, what's boiling point? All right, well, so melting, of course, is the process going from solid to liquid. And it's the temperature, the melting point is the temperature at which that process happens. Do you remember that when we're talking about the solid here, we're going, oh, okay, well, there's this fixed pattern, but they are still moving just a little bit. They're very organized when they're in the solid. When we're talking about a liquid, there's molecules, they're packed close together, but they're in a lot more random of fashion, and they're able to move. They move faster, certainly, than ones in solid. Then when we're talking about a gas, remember the boiling point is the temperature at which a liquid turns into a gas. They're completely separated. They can move at a very high speed. Please be aware, melting and boiling does not destroy a molecule and turn it into individual atoms. It changes the interactions between separate molecules. In fact, it usually destroys those interactions between the separate molecules. Just important to keep that in mind when we're going through and thinking about the boiling point and melting point. Okay, so I'm going to talk just about the boiling point, but be aware this also applies to the melting point. There's three things. There's the size of the molecule, the number of hydrogen bonding sites, and then really how polar or ionic a molecule is. So the size of the molecule. The larger the molecule, the higher the boiling point. It's really just due to an increase in the London dispersion forces. If I have a larger molecule, then I have more of an ability to do a bunch of those temporary dipoles all over the molecule. This is why when we're looking at methane's boiling point here, it's got a really low boiling point. In fact, it's so low that it's negative. That's why methane is a gas at room temperature. Same with butane, gas at room temperature. Hexane, you've actually worked with in class, and it's liquid at room temperature. And then octane, if we're also looking at octane itself, it's definitely also got a much larger boiling point. And that makes sense. If I'm looking at methane to octane, the number of carbons and hydrogens increases dramatically. So remember, that just means there's more spaces for those London dispersion forces. There's more areas where you could have those London dispersion forces. Again, with more hydrogen bonding sites, there's higher boiling points. So if we're talking about more than one hydrogen bonding site, then the molecules end up getting stickier. The more hydrogen bonding sites, then you can think of it as the harder it is to turn a liquid into gas. A great way of thinking of it is sort of like Velcro sites. If I'm thinking about something, for example, as this propylene glycol, this first molecule right here, and then glycerol, if I'm thinking about that second molecule right there. Well, the boiling point of propylene glycol is 188 degrees Celsius, and then glycerol is 290 degrees Celsius. The only real difference is just putting another OH on there. You can see that here, where there's 2 on propylene glycol, and then there's actually 3 on glycerol. Okay. The types of the intermolecular forces also greatly impacts the boiling point. So if you have a stronger intermolecular forces molecule, you have higher boiling point. You can also kind of compare this when we're thinking about if you're more polar, you can kind of think about that. Would you have stronger dipole-dipole interactions? Just something to think about. If you have stronger intermolecular forces, it's almost like the molecules are stickier. Again, just it's harder to break up those interactions between the molecules and turn it from maybe solid to liquid or liquid to gas. If you look here at diethyl ether, it actually has dipole-dipole as its strongest intermolecular force. It's a very polar, or it is a polar compound. So this oxygen right here, I know you can't see it, but it's bonded directly to a carbon. If we're talking about the hydrogen bonding, you have a carbon directly bonded to this oxygen, and then of course this oxygen directly bonded to just that change, just that simple change from putting the oxygen at the end or putting it in the middle, you have a very different boiling point. Look at that. You have 35 degrees Celsius for the diethyl ether, and then for butanol, you have a 117 degrees Celsius. That's pretty dramatic, and their weights didn't change really. You can also think about that with respect to when you get more and more and more ionic. Again, more ionic. Well, we know that since you've studied ionic compounds, they have higher melting points. In this particular case, you've got a pretty large boiling point. So just something to think about. Those types of intermolecular forces greatly impact the boiling point or the melting point. It also, of course, impacts solubility. So similar sort of things that I talked about for boiling points and melting points end up impacting the solubilities as molecules. Do also remember, like dissolves like. Polar substances dissolve in polar solvents. Non-polar substances dissolve in non-polar solvents. And I thought this was a really interesting video or figure to look at right here. So some of you have done this in class, but there's ethanol and water. You might see that the ethanol and water, depending on how you add it, it might float on the very top of water, which is kind of cool. But eventually it will mix. The ethanol itself, if you look at the structure of it, it's in your packet. If you look at the structure of ethanol, it has the ability to hydrogen bond, so it hydrogen bonds with itself. Water has the ability to hydrogen bond with itself. And because those attractions are similar, once you mix them, you can actually then have hydrogen bonding between ethanol molecules and water molecules. So they're able to actually mix freely and then able to essentially have them dissolve into each other. All right, this comes, of course, back to dissolving versus dissociating. So we've talked about sugar and salt a lot. Sugar is a great covalent compound to think about, and salt is a great ionic compound to think about. So when we're going through what's called the solvation process, which really just means that there's water molecules that surround a particular molecule of the sugar in this particular case, or if we're talking about it surrounding maybe one of the ions in salt. Solvation just means really being surrounded by water. The sugar crystal itself starts breaking up into little pieces once you put it into water. It starts dissolving. And all that's really happening is that the individual molecules of sugar, each molecule of sugar, is essentially getting surrounded by these water molecules itself. Now, a similar thing happens to salt, but remember we used that word dissociating before. So when salt dissolves in water, it breaks up into these individual ions. And you can also see, hey, look, the water molecules orient themselves in a very specific way around those different water molecules. Kind of cool to look at. I think this is also a pretty great one to look at as well. It's very simple, but it's just helpful to think of. When we're talking about ionic compounds, it dissolves and dissociates, right? So that means it breaks up into the individual ions. Sugar, not so much, just gets surrounded by water. It dissolves, but it does not break up into individual pieces. Just something to keep in mind. This is also really important to think about, again, back to melting and boiling. If I'm melting or boiling, I'm not breaking anything up into individual pieces. So just keep that in mind. Okay, now here's our must-try question. There's 3 molecules right here. Take a look. Predict which one has the highest boiling point, and which one seems the most likely to dissolve in water. And would that compound dissociate? You just want to write a very brief explanation. All right. Well, that's it for this video tonight, and we'll see you in class. Make sure you write down any questions, and feel free to ask your teacher more about this topic. All right. Have a good night.